Okay, great. Today I'm going to talk about reverse engineering human cooperation. And I want to start by just sharing a bunch of themes that have been kind of present throughout the workshop this week. The first is this idea that cooperation is ubiquitous across the animal kingdom. So here's an example of weaver ants, which was actually talked about earlier this week in the workshop, building a bridge to cross a gap in their navigation that no individual ant would have been able to cross on their own. Other examples include packs of animals that hunt collaboratively to take down prey that one wouldn't be able to catch individually. And then furthermore, as machine intelligence starts to become a reality, we're faced with new forms of cooperation between machines and between machines and humans, different ways that these systems may operate together to help each other and hopefully help us. But really, I want to kind of push on this idea that human cooperation is in many ways distinct. So this is a famous experiment from Burdick and Tomasello. Even a young child can cooperate with a scale, scope, and sophistication that exceeds all known non-human intelligences. Toddlers barely able to walk can spontaneously help others to complete tasks. 3-year-olds share resources and divide the fruits of their labor fairly. And I actually was quite lucky. I have a 19-month-old, and I wanted to replicate this experiment. So this is a new result from a few weeks ago. This is one of my new grad students, KJ, and Natasha, my wife. And so we're replicating Tomasello, and here he goes. So just like in this is truly zero shot. Although I will say he just stood there saying books, 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 and we had to say, Nathan, do you want to help? So we didn't tell him what to do, but just said help. So it was good theory of mind, but maybe not spontaneous altruism just yet. Okay, so. All right, so we have this incredibly distinct way of cooperating even from a young age, and those basic cognitive feats give rise to what's sometimes called the human singularity, right? Our ability to form unprecedented levels of cooperation in terms of social institutions, social contracts, businesses, governments, science, technology, morality. In some cases, these cultural products will involve millions of unrelated individuals in different locations who will never meet. And the questions I'm really interested in are, what are the origins of our social intelligence, and how does it distinguish humans from other animals? And then how can this knowledge be used to design machines that are equally capable of interacting with humans? Okay, so I was also really lucky to get to follow Joel because he introduced so many of the main themes of this talk, and I'm going to be building off some of the concepts that he's already introduced. So this is a great start. All right, so cooperation is great. It's this powerful force for us to achieve all sorts of impressive feats as individuals and as a civilization, but it's incredibly challenging. And the challenge comes from the fact that even though collectively we can all be better off if we cooperate, individually we might be better off if we only look out for ourselves, right? And so this has sometimes been called the tragedy of the commons, where by doing what's best for oneself, one kind of leads to a situation where everyone else is worse off. And essentially, there's been now almost half a century of research or more on how to reconcile this tension. We see widespread cooperation across both the animal kingdom and human society, but we have this logic, this individual logic of both of evolution, of economic rationality and agency. And this has really been a question that many have studied in a variety of different fields. And in particular, evolutionary game theorists have spent a lot of time thinking about this with formal models. And one place they start is with a game like The Prisoner's Dilemma. And Joel already introduced a game just like this, so I can go a little bit quicker. But the basic idea is that you have a bunch of different possible payoffs to two players, and both are better off if they cooperate. So mutual cooperation is best for the group, right? We see that the two payoffs are the two numbers in this grid, and the two numbers are highest collectively when they both cooperate. Now, one could do better. You can set 8 is better than 7 if you compete. If you kind of defect against your opponent, but they do really poorly. But if you both compete, you both do worse off, right? So this is in some ways has become kind of like the Drosophila of the social sciences for studying questions of cooperation. It's highly distilled into this one specific way of looking at the problem with just two actions, and really highlights that tension between cooperation and competition. Now, in the one-shot version of this game, there really is no cooperation. You play the game, you never see the person again, and there's really not much that can be done in that anonymized one-shot version of the game, except to defect or to compete. But when the game is repeated many times, we actually see something quite interesting. And so this is the experiments of Robert Axelrod in the 80s. They ran an evolutionary tournament with a repeated prisoner's dilemma. And the strategy that emerged in the winner of this tournament was a strategy called tit for tat. And it's a really basic, simple idea that led to a certain kind of reciprocity in the repeated prisoner's dilemma. The idea can be described in a single sentence. Start off playing cooperate, and then copy whatever the move your partner played in the last round. So if they respond, if they cooperate with you, you cooperate back. If they compete with you, you compete back. So it's tit for tat. Okay. Now, this idea of tit for tat, I think is, it seems quite rich. It seems like it captures some of the aspects of cooperation, but in many ways it's relatively impoverished. So something like tit for tat really only can talk about a two-player game like this with just two actions. The strategy doesn't know anything about the payoffs of the game or what welfare is going to be assigned to different players. It just knows the labels, C and D. And in fact, it doesn't even know that. It just knows play row 1 if your partner played row 1, play row 2 if your partner played column 2. And when you change the game and you say, okay, well, I don't want to study Prisoner's Dilemma, or I want to change it so that it's, instead of us both acting at the same time, we're going to act sequentially, or I'm going to add noise so that sometimes when I want to cooperate, I compete, tit for tat no longer is the right strategy to play. So what the last kind of almost 3 or 4 decades of research, and actually there was a paper in Nature that adds to this zoo of strategies. Basically, I'm showing all these different kind of automata-like strategies that try to say, well, here's the strategy that might work in this other variant of a cooperation dilemma. Okay. My goal is in some ways different, right? I want to reverse engineer human cooperation, and I want to understand how we can think about the concept of reciprocity and cooperation more broadly in much more general and abstract terms that allow for general cooperation, or the idea being cooperation across a wide variety of situations with a wide variety of partners. So in particular, I want to ask these two kind of key questions around reverse engineering, which is, what are the cognitive processes that underlie social intelligence, and how do they contribute to the scale and scope of our cooperation? And then how can this knowledge be used to design cooperative artificial intelligence, equally capable of interacting with people? And in some ways, as Martin Novak said, we're super cooperators. How do we go from this basic tit-for-tat form of cooperation, which can be implemented in a yeast cell, to something that is distinctly human, that explains the ways in which our social intelligence is different? Okay, so in contrast, we start by saying, well, the repeated prisoner's dilemma is not enough. And this is work with Alejandro Vientos, David Rand, and Josh Tenenbaum, where I did my PhD with, where we looked at something we call a game generator. So instead of playing one game many times, instead we're going to look at playing many games many times. And so the idea here is that you're not just playing one game over and over again, but rather you're playing a whole distribution of games that comes out of a generative model. So each sample from this generative model is a different kind of social dilemma, right? We can generate games with nearly infinite variety. It can generate situations where there's only one option available, and you have different options. So here's like a donation-style game where player I can just pay a cost to themselves to give J some benefit, or allocate rewards between I and K with no cost to themselves, or some combination of the two. And by composing these different games, we have all sorts of different structures that all sorts of different kinds of games that can emerge. Things like the Prisoner's Dilemma, like the Ultimatum game, a whole suite of things that game theorists haven't even studied today, all in this kind of with infinite variation over what kind of payoffs there will be and the number of actions that will be included. Now, because of the variation in the games that are being generated in this environment, I think it's implausible and impractical to imagine that people are learning a specific strategy for each one, right? So it's not like, oh, well, when the game looks like this, I'll play tit for tat, and then here I'll play win, stay, lose, shift, or some other strategy. Instead, we're looking for a general principle of cooperation that can play all of these games. Okay, so if we kind of think back to the problem of in the 70s and 80s, which was how do we get cooperation in something like the Prisoner's Dilemma or the repeated version of it, and the answer looks something like tit for tat. What I'm going to try to figure out in this talk is what's the answer to what cooperation looks like in this environment. Okay, and I want to start with what might be kind of a kind of basic insight coming from cognitive science, which is that people don't just make decisions based on simple rules and heuristics. They actually evaluate consequences and look at the payoffs of the game. And a traditional way of doing that is by introducing the idea of utility functions. So we're going to look at the evolution of, instead of looking at the evolution of automata or strategies, we're going to look at the evolution of utility functions. Okay, so what can we write down? Let's start with some really basic ideas of how we might value outcomes in one of these dilemmas. The first is to think about what would a selfish agent do? An agent that only cares about its own individual welfare. Well, the utility of that agent would just be the reward that it gets. So the utility of agent I is equal to the reward received by agent I. Now we can think about, okay, well, no reason to think that that's going to be very cooperative. What would a more pro-social agent do? So we can think about these kind of various forms of, you might even think about this as a kind of utilitarian kind of model, right? It's just altruistic, but it's just kind of unconditionally altruistic, right? So it cares about its utility is the reward that it receives, and also the reward that everybody else receives in a particular state. Okay, so how might we decide which of these utility functions is better than the other? Well, what makes a utility function rational or well adapted? Is it the one that achieves the best outcome when playing against itself? So like this altruistic agent is going to do really well when it's matched with another altruistic agent because they're both going to pick that a cooperative action. Or what about when it's playing against anybody else, right? So this selfish agent's optimizing for its own success, and it might take advantage of this altruistic agent, which will be highly giving. Yes?
It's natural to multiply the IJs by some coefficients which measure how much you care about that individual.
Yeah. So we're going to get there. Yes, absolutely. This is just to kind of set, and those kinds of pro-social utility functions have been studied extensively, and I'm going to get to exactly there. Okay, so how do you decide which logic is the right one to apply here? And I think the key idea here is that in a multi-agent system in the social world, the environment itself is adaptive, right? You're not just optimizing against a fixed landscape or a fixed environment. You're actually optimizing in some ways against what all the other players are also doing. And that itself could be changing or evolving as those players adjust their strategies. So here's what that looks like in a very kind of schematic or simple way. Imagine we start off in a world where all the players are altruistic, right? So the total welfare, or the average welfare of any individual in this world is actually really high. It's as high as it could be. Now imagine there's some mutation, and one of these one of these players becomes a selfish agent, adopts that utility function. Well, it's going to somewhat lower the welfare of the whole average welfare, but this guy is going to do really well because he can exploit all of these other altruistic players. And over time, if we apply a kind of natural selection-like logic, what we'll see is that the environment slowly becomes composed of more and more selfish agents, and we end up in this kind of sad state where we're experiencing the lowest possible average welfare. Okay, but not as all lost, right? So Steve Pinker writes, natural selection doesn't forbid cooperation and generosity, it just makes them difficult engineering problems. And that's sort of the approach that we take here. So we have this kind of base case of this selfish and altruistic agent. We've also studied other simple forms of pro-social preferences. But we are going to look at a new solution that has a bunch of desirable properties that hasn't been explored yet in this literature. There's actually very little work on the evolution of utility functions in general because they aren't tractable in the same way that automata are. And importantly, and I'll kind of unpack where that is. So what we do is we introduce a new kind of agent. We call it the Bayesian reciprocator. And the Bayesian reciprocator is designed to weight the payoffs so it cares about its own welfare, right, the reward that it gets, and it cares about the rewards that other people receive, but it weights that, exactly as was mentioned, by its belief that agent I believes about agent J, that the utility function of agent J is equal to its own utility function. So it has this sort of reciprocity, but in the space of its own causal function of action. Okay, so it has this key belief term that's going to weight utility functions. Agents that it thinks are also a Bayesian reciprocator, it will weight highly and act altruistically towards. Agents that it believes are not a Bayesian reciprocator, it will not weight their utility and will act selfishly towards them. Now, the challenge and kind of the main innovation in this work is thinking really carefully about how to make this work. Yes?
So in this kind of like selfish, unselfish regime, this makes sense. In other kinds of economic regimes where I actually don't want my partner to have the same utilities that I have, because then we all want the same thing. Then it's I want them to have different desires, and so the matching thing seems odd in a generalized exchange setting where I actually want like an ecology of complementary values that are not stacked up. In fact, that's like kind of the worst possible world.
Yeah, this is like we all want the same resource, or like
and I'm gonna value people as a function of their ability to compete with.
Yeah, I think that's a great point. The way I would kind of abstract this is say, let's say there's two levels of the utility function. One is the weights over the things in the world that I actually care about, and then there's on top of that the social preferences, which weight how much I care about different people. And I would say you only want to do this matching at the social preference level, not at the world feature level.
Even then, I can talk about settings in which you want other actors to behave in ways that you wouldn't behave. Okay. And that's in fact what checks and balances and institutions are, is that they don't all behave in the same way to kind of accomplish global utilities. Anyway, it's
cool.
fine.
I'd love to hear some of those examples. But yeah, no, I think that's an interesting point. And we are looking at, just to be clear, we're looking at very abstracted utility functions where the only thing that you can value is basically kind of like a single welfare number. So a lot of those details are going to be abstract. Okay, so you have this belief term, and the kind of key idea here that we have is that this belief term is going to require a kind of theory of mind. So it's going to require the ability to learn from people's interactions or the kind of behaviors that they choose to infer what is their utility function, right? The utility functions of other agents and other players are never observable. We don't know anyone else's true preferences, but we can learn about them from watching them interact. And I thought just for this audience, it would be good to kind of give a kind of vivid, or one of what I think is a very vivid demonstration of theory of mind with this classic stimulus from Heider and Simmel, where you see different shapes interacting, and maybe just watching this for a few seconds, and if someone wants to volunteer what they're observing, what do you see in this video? What was that? Triangle bowling. Okay, great. So that's all we really need to hear, right? We see a few shapes moving around, and we infer a bunch of complex hidden mental states, right? That the triangle is negative, they don't like the circle, and they're bullying, they're stronger. All of these inferences, I think, are great inferences to make, but nobody is talking about the pixels that are moving around on the screen. And nobody said, and when I give this demo, no one would say, oh, the triangle moves a few inches up and then it moves to the left, right? That's the wrong level of explanation. Theory of mind is the ability to go beyond the data and infer those hidden mental states. And that's exactly what we're proposing that these models need to be able to do. Okay, so how to model that formally? So we have these three types of agents. This one requires theory of mind. And what we do is we take an idea that I and many others have used in a lot of different work in studying people's social intelligence, which is the idea of a Bayesian theory of mind. And I'll just give you kind of a high-level sketch of what this looks like. The general idea is you need to really first define a model for action. This is a kind of a generative model of an agent, which says, if I assume that agents act probabilistically, and I want to know, given the type of, and I need to know, given the type of an agent that you are, what's the probability that you'll choose a particular action? And this basically just says that you're kind of softmax rational, that you're going to choose roughly proportional to how good that option is for this particular utility function. Okay, so then what is theory of mind? And what does a Bayesian approach to theory of mind look like? Well, it's just kind of using Bayes' rule to rewrite this and using this as the likelihood. So what we want to know is, what's the probability that you have a particular utility function given all the actions I saw that you take? And we can write that as just the probability of a particular action, of each action that you took. This is the model of action, with some kind of prior over the probability of the type that you are. Okay, so this is built based on almost a decade or more of work thinking about Bayesian theory of mind, and we're really the first to look at it in this kind of multi-agent interactive setting that requires agents reasoning about each other at the same time. Okay, so let's see how this plays out in a simple example. So we're going to have a few agents. The first is agent A, and or actually, let's do this from the perspective of, this is from the perspective of an observer. So this is us. And this is our prior over agent A. And so we start off, okay, maybe I'll start with some prior that they're more likely to be this Bayesian reciprocator type. And we're going to play a game where there's two actions, just to make it simple. You can pay one to give three, so you pay a small cost to make a bigger benefit for somebody else. Or you can just do nothing, right? Like, so pass, I'm not going to be nice to you. And let's say we see A give to B. Well, that's going to update your belief distribution, right? You're going to say, well, they're either altruistic or a Bayesian reciprocator, but they're very unlikely to be this selfish agent, because the selfish agent would never pay a cost to help someone else. Okay, what if we see that agent A play keep when interacting with agent B? Well, it's the opposite, right? Very unlikely to be this Bayesian reciprocator, definitely not altruistic, very likely to be selfish. Okay, but now let's play this out a little bit more, right? What happens if we've seen agent A play keep with agent B, so we think agent A is likely to be selfish. And then we see agent B play keep back to agent A. This is sequential, right? Well, if we just naively apply this idea of Bayesian theory of mind, we get something that doesn't make sense, right? Which is that B, we infer that B is also selfish, because in our naive version of theory of mind, you're just a selfish person plays keep, and altruistic player or Bayesian reciprocator would play cooperate. But that's not quite right, right? We need to have a model that updates what B thinks about A, right? That's the important key piece here. Okay, so we need to have a recursive theory of mind. So not just modeling what we think about A and B, but also what A and B think about each other, right? Okay, so we have to unpack this and unroll it. And that leads to these giant tree structures of belief that have been studied pretty extensively. Sometimes they're called level K models or cognitive hierarchy. But what you can see with this tree is that it basically explodes very quickly, right? The longer the depth you go of me, A, thinking about B, thinking about A, it can go kind of ad infinitum, as well as you add more agents, this is going to get really wide. And so this blows up very quickly, and at best, you're just approximating the thing that you actually care about. So what we do is we say, well, what if there's a different representation of belief, which is a kind of joint belief? And instead of modeling what A knows about B, you're modeling a kind of joint belief, meaning, what do A and B both know? You can think about this as, the key observation to get to this is that A's model of B's beliefs only depends on the events jointly observed by A and B. So A's model of B's beliefs should then be identical to the beliefs of an external agent, kind of in a third-party perspective, that they would form had they just observed what was jointly observed by A and B, right? So instead of building this kind of nested hierarchy of beliefs, we can condition on what is often called a kind of common knowledge or joint belief. And this drastically simplifies reasoning and updating knowledge about beliefs in large groups. Okay, so what does that look like? So here was our problem, right, where when A was mean to B, we thought they were selfish, but then when B was mean back, we thought they were also selfish. When we replace the naive theory of mind with the recursive theory of mind, we get what we expect, which is that when B basically keeps when playing with A, well, there's still some probability they're selfish, because that's also consistent with what a selfish agent would do, but it's also quite likely that they're a reciprocator. They're reciprocating the fact that that A didn't cooperate, rather than just kind of optimizing for themselves. And you could do the same, show the same phenomena. You get the wrong thing here. If B gives back to A, well, that's not very reciprocal, right? That should be more altruistic. When you add the recursive theory of mind, that's exactly what you get. Okay, so so kind of unpacking, that's how the belief updating works in our model. And here's kind of just zooming out a little bit how the model works overall. Start with priors over the utility functions of other players. You act based on those beliefs, so you choose an action in the particular scenario that you're faced with. You observe the behavior that occurs, either your own or the behavior of others, because even when you act, you have to update what other people think about you, right? And then you compute the likelihood of that behavior under your generative model of others, update your beliefs over others' utility functions, and then you're ready to act again in the next round. Okay, so I showed you what belief updates look like in a stylized setting, but we can look a little bit more quantitatively. What happens when this Bayesian reciprocator is paired with different agent types that it doesn't know their utility function? So here's after an example of looking at their beliefs across these three types after 20 interactions. And you can see when it's paired with the selfish agent, in just a few interactions, it's very confident that it's learned this is a selfish agent. And with the other agent types, it's learning a lot slower, right? It's hard to disambiguate a Bayesian reciprocator from an altruistic player because they both will start off cooperating and cooperate for a while with each other. So this is actually relatively slow to learn in these environments. Okay, so the belief updating works. It can reliably recover, at least to some extent, the underlying types of these agents. And most importantly, it can figure out who's selfish, because that's the important person to not be cooperating with. Okay, so then next we study we actually look at these in an evolutionary simulation. So we take our game generator environment, and what we're going to do is we're going to study the steady state of the population distribution of the steady state of a population of agents under the Moran process, which is a simple stochastic process that describes is kind of a simple model of an evolutionary replicator. Basically, in each generation, one player dies, and then it reborns, and the new player picks its type proportional to how well the other types did. So types that do well are more likely to be copied in the next generation. It's a model of both biological and cultural evolution. We study this in a small population. This is like where cooperation often is quite challenging. And we're going to look in the limit of small mutations to make these analyses tractable. Okay, so the first result is we're going to vary how long the game is. So between a pair of agents, how often do they get to play in the game generator together? And so we're varying that on the x-axis. And now, as you'd expect, when you're just playing like a one-shot game, you don't get any cooperation. So red is showing the selfish agent. But as the game gets longer, the Bayesian reciprocator shown in blue becomes the most prevalent type. Because the way that these models update their beliefs, it works quite well probabilistically, right? So as we add error, I tried to play one move, but a trembling hand moved me to do something else. Our agents are still able to be quite robust to these errors. They're able to account for the fact that you can think about it as robustness, you can think about it as forgiveness. You played something that looks selfish to me, but I'm going to let it go. And there's a nice kind of dynamic here, which is if you defect on me early on, it's going to have a much bigger effect on my belief state than after we've already successfully cooperated many times, right? So that's, I think, one of the reasons why these models are robust. We can look at these two together, and they kind of trade off nicely. More error in the simulation requires a longer game length for cooperation to evolve. Blue is the cooperator, the Bayesian reciprocator. And just kind of prove to you these guys are cooperating, here's the average payoff of the population, and the areas where there's a lot of Bayesian reciprocator is where the payoff of the game is quite high.
Can I ask a clarifying question?
Yes, of course.
So game length is the thing that determines the payoffs that feed into the Moran process. So we play 9 games that assigns the payoff to people, then we do it. Okay.
That's right. That's right.
So this is what we're looking at is the sort of like long run.
And then, yeah, so if it's game length, yeah, good. So if it's game length 3, it means everyone plays 3 rounds with every dyad. We see how well everyone's doing. Next generation, 3 rounds. Yeah. Yes.
One more clarifying question. So, if a player at the end of this has some beliefs about other players, when they die, those beliefs die with them, and you have a new player come into existence who may be starting from some higher set of beliefs. Is that what's happening?
Great question. At the end of every generation, all the beliefs are reset. Basically, everybody dies, but almost everybody just reproduces their exact kind, and only one person has the opportunity to change types. That's just how the Moran process works. You can change those assumptions, and it's roughly similar. So all the beliefs are reset after the end of the interaction.
It seems like the prior beliefs then would matter a lot in what happened.
Yeah, I didn't include that graph here, but a reviewer asked for that, and they actually don't matter that much. And part of the reason for that is that the prior matters very early on in the game. But early on in the game, cooperation is not possible. So the prior ends up being somewhat washed out by the time that cooperation is even possible. So that's what we find empirically, that it does matter kind of on the margins here, but less than you would think, as long as it's not super extreme. Yeah.
I just wanted to ask more about the game generator. Like, what distribution of games is it producing?
Yeah. So
all social dilemmas, or what is the?
No, it's not. So it's not all social dilemmas. It basically, I can go all the way back, or just it basically samples different. There's sort of 2 dimensions of variation. One are how the agents are going to which agents are going to interact with which ones, and it can be between I guess 2 and either 2 or 3 agents are involved, and then we randomly sample costs from a continuous distribution. We randomly sample benefits from a continuous distribution, and those are then set to the different players. So
is it like observing the game or something, or how does it know what is?
Yeah, it observes the sample. So sorry, each interaction is a sample from that game distribution. So there's no uncertainty about what the payoffs are once the players are actually interacting with each other. Yeah.
Do all the games have direct interaction between players? Are there pooling games?
No, they're not pooling games. That would be cool to look at. But as long as you can evaluate a utility function over the outcome, all the same things should hopefully would still apply. Okay, great. So this is I think this is in some ways this is good news, right? We can find in a game in a kind of environment where the game, you never play the same game twice, we can still cooperation can still emerge with the right kind of utility function. But what about a different setting? So here, all the interactions that you observe are ones that you are a party to. You either were the one who made the choice or the one who could have received some welfare. That's this typical repeated prisoner's dilemma setting. But another important setting is one where your behavior is not private in that sense. It's actually public, right? So when a player takes an action, everybody gets to see what they chose. And the dynamics of learning look quite a bit different, right? So here, in a small population of agents, we're looking at the beliefs of the average beliefs of a learner watching a small population of agents interact. And what you can see is, again, they do learn the types of the different agents, but it's a little bit harder to learn the selfish agents, but it's easier to learn who's altruistic. And the intuition there is that if I can observe other people's interactions and I see someone who keeps cooperating with someone who's not cooperating back, that's a good indication that that person is not a reciprocal agent. So it actually helps distinguishing these 2 types from each other. Okay, now we can look again at evolution in a setting like that, and this is sometimes called indirect reciprocity. So we look at a setting where each player interacts no more than 1 time with another player. So you never play the same game twice, and you never play with the same person twice. And you can think about here is the beliefs that you're forming kind of are a great way of integrating across those 2 forms of experience. They kind of become a measure of reputation for what you think these players are going to do. So here we're varying the probability of observation. So at 1, all observations are public. At 0, we're back to the kind of everything's private, and we can kind of vary that continuously. And you can see that observability is really important. Once you are fully observable, we can still recover. We can still have the emergence of cooperation happen. But as this probability gets lower, it eventually falls off. Again, this is just showing when the blue Bayesian reciprocator is most prevalent, there's a high payoff in the population. That's close to the maximum payoff. We can look at different forms of error. So again, like this is the probability of action error paired with observation. So if you make errors more costly, you need to have more observability to make up for it, right? And again, showing there's some kind of set of parameters where this works well. And then this is a different kind of error where instead of making a mistake in the action space that everyone agrees on, I have a perception error. So I think you cooperated, but you didn't. And that's really challenging for some other kind of baseline models because the beliefs then get kind of, we no longer have the same beliefs about reputation. And you can see, so this, we're robust to small amounts of error here, but it becomes less robust over time. Okay, so I showed you, yes?
Do agents know the probability of observation error?
Yes, they do. So they're able to use that in their conditioning. Yeah. Okay, so what I showed you, I introduced this new environment, and I introduced a new player that could do well, and cooperation could emerge using this new player in the environment. And one thing we were excited to test was, well, what happens when we take the Bayesian reciprocator back into the kind of canonical setting that everyone studies, the repeated prisoner's dilemma, the iterated prisoner's dilemma? How does it fare against all these other well-known strategies? Okay, so we tested against a wide variety of different strategies. First, we looked at kind of like the greatest hits of the last 40 years. So you have these kind of unconditional strategies, always defect, always cooperate, always the kind of still the like gold standard of defection. Tit for tat, the one I talked about before. Generous tit for tat, which has a little bit of forgiveness, so it will sometimes forgive defection. That's important for error correction. Forgiver is popular in the sequential prisoner's dilemma. I don't have to get too much in the weeds for this unless people are really curious. Win, stay, lose, shift, also a very, very popular strategy, has error correction and can kind of do a little bit of exploitation. And then these are these new extortion strategies that try to force an opponent to kind of take what it, kind of can force a learning player to take less than it receives itself. Okay, so here's what this looks like. At first, I'm going to show you simulations that don't have the Bayesian reciprocator, just to show you what the baselines look like. So here we're looking at error rate, and you can see that most of the region is red. That's always defect. And then there's this yellow sliver here. So for small errors and longer game lengths, win, stay, lose, shift emerges and enables cooperation. Now we're varying the cost benefit. So looking at what if the benefit of cooperation is lower. And again, you see this like sliver of cooperation where win, stay, lose, shift is the dominant strategy. This is the simultaneous prisoner's dilemma, the one that we've been talking about. But we also can look in the sequential prisoner's dilemma. This is one where I act, then you act, and we go back and forth. And again, it's a different strategy now. It's this forgiver strategy. And again, there's a small sliver where the forgiver strategy is prevalent and cooperation happens. Now we add the Bayesian reciprocator into these simulations and look at what happens. So first, in the case where we look at error. So we find, first of all, that the Bayesian reciprocator outcompetes all of these automata strategies, right? The yellow, the orange is gone. And second of all, that we've drastically expanded the scope of cooperation, right? So there's a lot more blue than there was orange. And that's true when we look at benefit, and it's true also in the sequential iterated prisoner's dilemma. So you can see the region of cooperation has grown substantially. And I'll show a little bit more to that effect again. Now, we wanted to look at a more kind of systematic set of automata. So we then next look at all memory one strategies. And there's good reason to just look at memory one strategy. I can go into probably after the talk. There's 26 of them in total. And here now we're just going to look at payoffs because there's too many strategies to look at all at once. So here's what the payoffs look like. And it's very similar to before, right? So without the Bayesian reciprocator, you have this sliver where payoffs are high, meaning cooperation is happening. And same with benefit, right? There's this region here where benefit is high. Same thing with the sequential prisoner's dilemma. You have this sliver here and this kind of gradient where cooperation is possible for different cost benefits. Now we add the Bayesian reciprocator and we see two things. One is that region of high payoff for the population is much bigger. And second of all, it's much darker. Meaning here, yes, those cooperative strategies did emerge, but they were always in competition with the defectors and kind of in some ways kind of going back and forth. That doesn't happen with our strategy, right? It's extremely cooperative when it does evolve. And we see the same thing with benefit and the same thing across these two kinds of environments. When we look at the kinds of strategies that evolve, I think I'm good. We see that there is still some region where we do see some of those nice automata. Nice automata are automata that cooperate on the first move and respond to cooperation with cooperation. So it's a way of clustering those 26 strategies. The not nice ones are basically everything else. So you can see here's the not nice region, the Bayesian reciprocator region. And there's a small region where the automata strategies are still the best ones. And you kind of see the same results, again, for all four different settings. Okay, so I hope that in some ways this result can help us understand the power of theory of mind. And I go back to this really kind of revolutionary work from Preston Dyson in 2012, where they introduced a kind of key dichotomy for thinking about the evolution of cooperation. They said, there's an evolutionary player. Those are these memory one automata players. But there can also be, they imagined that a theory of mind-based player that infers the strategy of others could also exist, that was kind of outside of the scope of their analysis. And they hypothesized in this work that the player with a theory of mind could resist extortion and other kinds of manipulations. And they concluded at the end of the paper, it is exactly evolution on the hugely larger canvas of DNA-based life that ultimately has produced player X, the player with the mind. Okay, so I think in some ways, that's what we tried to do with the Bayesian reciprocator. It's a new model for understanding the emergence of cooperation, and it really leverages theory of mind for a distinct cooperative advantage. We quantify the advantage in evolutionary game theoretic terms, and I hope, kind of thinking most broadly, that in some ways that it can explain why humans, who have the most sophisticated cooperation structures and we're the most sophisticated cooperators, we also have the most sophisticated machinery for understanding the minds of others, right? So it's really these two things put together that maybe can explain somewhat of our the scope and scale of our cooperation. Okay, yes?
I want to just sort of test my intuition about sort of evolutionary stability kind of questions. So is it the case that the error is beneficial for the Bayesian reciprocator because that allows them to distinguish some of the other nice agents from themselves? So, because it seems like if you had a population of all Bayesian reciprocators, they could be invaded on no error by these always be nice strategies or whatever, but it's important for them to be able to purge those folks, since too many of them would then allow the defecting type agents to invade. So is the intuition right that error is actually sort of good for them because it generates behavioral variability that allows them to differentiate between themselves and naive cooperator types?
Yeah, we haven't studied it with the formality I would like to, but that intuition I think is exactly right. And we have done some preliminary experiments because with the exact logic that you're saying here is that you might imagine that there's kind of an explore-exploit dilemma here, which is it might be to my advantage to try to learn who's who and maybe take some exploratory moves to probe the space and see how agents respond. And we've done a little bit of that of making the agents more or less noisy, but I think it deserves the kind of a fuller treatment. But I think that intuition is right. Yes?
I'm not sure how you can come to the conclusion that this explains the scale of human cooperation, because it seems to only work if I have a theory of mind of everyone. And so as you blow up the population, it becomes less and less realistic that I have a theory of mind on all sorts of different individuals. And so for large-scale cooperation, I feel like these sort of individual-based approaches might not work. I just want to know what your thoughts are.
I agree. One thing I will point to is just this joint belief structure I think is quite interesting for generalizing. Because even that is exactly as you're alluding to. Everything that's individual based is going to blow up. But the joint belief structure kind of gives a little, this way of thinking about it, gives a way of then saying, well, how might we abstract the idea of a bunch of agents interacting with each other? We might think about them as groups. Can we update, what does a certain group believe, or what do I believe about a certain group? That would be one, I think, really cool extension to get at exactly your question. We haven't done that. Yes.
Really, really cool framework. I think the data you're showing us is super fascinating, concrete, and you can see how tweaking different knobs in your framework help generate different things. I'm just wondering if you've thought about, it's kind of related to an earlier question about how there's an assumption about basically U is equal to UI, the belief that other agents have the same utility function as me. One could imagine defining other relations other than equality between utility functions. Have you thought about doing that?
Yeah. So equality is a very strict notion, and I think we're taking advantage of the very discretized space of utility functions to do that. Realistically, it's probably going to be something softer, something more similarity-based, including all the kind of just figuring out which portions of the utility function are the ones which are important for reciprocity to act over versus which ones are irrelevant, or maybe even, as James pointed out, ideally different. If you like apples and I like oranges, we don't want to have a reciprocity based on that distinction. Yes?
So I'm an experimentalist. I get data network is super cool. How do you test test that? How do you validate that experimentally? Because I don't.
Yeah, I think so. Absolutely, yeah. I mean, so the evolutionary parts I think are harder to test experimentally, but we have a lot of really clear predictions about belief updates for a theory of mind, right? So we're starting to kind of design experiments that show, hey, if you see these two agents interact and one chooses this action, what do you believe about these types, and what's more, or make predictions about their next action? Those kinds of experiments are highly tractable for testing experimentally. Yeah. Okay, let me go on because I have a kind of a whole second part that really builds on some of the framework that Joel set up. Okay, so Bayesian theory of mind, it's really great. It powers cooperation, and I thought I'd just kind of allude to a bunch of other projects I've worked on that leverage Bayesian theory of mind and in the context of cooperation. And the kind of general recipe has been find a richer task. In this case, I showed you about the game generator, and then build models of how people play that task, kind of these computational cognitive models, oftentimes with empirical data, to your point. So we've looked at when to cooperate, when to compete. We've looked at when do you signal, or how do you signal cooperation to show you're a cooperator. We've looked at when it's more than two players, you might cooperate with a group of people to compete against another group. So how do you cooperate to compete? We've looked at how people structure cooperation, so divide and conquer versus working on the same task together, collaboration with James. And we've also used these same ideas to build reinforcement learning systems that can perform superhuman cooperative AI, although in this game Avalon, although it was done in 2019, so there was no communication or language. Okay, so kind of cooperation's been this has been a really rich area of research for me, and the second area of research I've spent a lot of time thinking about is going from cooperation to morality. So we have these social utility functions like the Bayesian reciprocator that I showed you. And you can kind of think about, it's a way of telling us how should we treat others, how should we integrate the preferences of others into our own value system. And you can kind of think about it as a kind of proto-moral system. Now, of course, there are many other important kinds of moral reasoning, some that can be captured in utility functions that don't look anything like this, and some that don't look like utility functions at all. So I've done work on fairness and inequality, looked at the role of intention in structuring, in deciding whether an act is permissible or impermissible, and also looked at moral learning, so how different, more complex systems of values might be acquired. But what I wanted to talk about was some somewhat recent work led by Sidney Levine on a kind of moral reasoning called universalization. And this directly connects to what Joel talked about in the last talk on equilibrium risk. Okay, so what's going on here? Let me start with an example. I'll give you a brief example of what these kinds of experiments look like. So, I've now had the privilege of studying various kinds of phishing dilemmas multiple times. One which unfortunately didn't make the talk with Kelsey and Toby, but here we're going to have another phishing scenario. We have 20 vacationers, and they're on a lake, and they all fish the lake in a sustainable way. Okay, but then a new fishing hook comes along, and it allows each vacationer to catch many more fish than they would be able to otherwise. And in a variety of different experiments here, we vary what is like the threshold of fish that can be taken for the lake to sustain its stock of fish. So if 3 vacationers start using the new hook, there's going to be no negative consequences. It's fine. So as long as a small number of people use the new hook, that's okay. But if more than 7 people start using the new hook, then over time there's going to be a total collapse of the fish population. And in between, it's like maybe it's okay. Some people can use it as long as you're in that world. Okay. So then the question you should ask yourself is is it morally acceptable to start using the new hook? So think about that for a second, and I'll give you a few more kind of knobs to tune on this example. And we studied many variants of these kinds of tasks. What does it matter if there's high interest? So if 19 of the 20 vacationers all want to use the hook, versus if nobody else besides you want to use the new hook. And then ask yourself, is it morally acceptable to start using the hook if you know for sure that none of the other people, regardless of their interests, will actually do it, right? So this is, I think, a great example of this kind of equilibrium selection problem, right? You know that no one's going to use it. So you know that your choice to use the new hook is not going to lead to collapse. But I think many of us might share the intuition that it's still wrong to do it, even though there won't be a direct, at least an immediate harmful consequence of that choice, because I think of the kinds of things that we've been discussing, that might lead to a change in the equilibrium of these 20 vacationers. Oh, if they see one person using it, then in the high interest group, all 19 will be like, well, if he's using it, I'm going to use it. And in the low interest group, that doesn't seem to be as much of a problem because no one else wants to use it. Okay, so this is just one of many experiments from this paper. Basically, we show that in the high interest group, it's not very acceptable to use it. In the low interest group, most people think it's okay to use it, right? Okay, so hopefully you have some of those kinds of intuitions. Yes?
So are you trying to filter for certain kinds of morality? I mean, this feels like you're kind of, like all the moralities you're describing are kind of universalist utilitarian versus like a virtue ethics or a deontological. I mean, this seems like it selects in a very certain kind of morality framework.
Yeah, so I mean, the goal in this paper was really to push on that kind of point, which is like universalization. It's a new bucket. It doesn't fit into rule-based thinking like deontology. It doesn't fit into utilitarian type thinking. We have a bunch of different, where we implement all the models and compare them. But I don't want to go down that route. This is the last slide on this particular project. I just want to kind of show you this idea of universalization, which is kind of an interesting and potentially powerful mechanism that humans are very capable of using. I loved the AI restaurant booking example, which I think we do naturally ask ourselves, what would happen if everyone did what I did, right? This question of what if the equilibrium changed? The kind of origin, maybe as a side note, one of the origins of this project was I was in Mexico, probably I guess it was 10 years ago, and I saw there was like some Mayan ruin, and this like 5-year-old went to like try to touch the statue, which was like behind a rope, and the mom was like, no, don't touch that. What if everybody touched it? It would be ruined. And I was like, that's interesting, like this really interesting way of expressing a moral principle, especially to a kid. Actually, in this paper, we have some developmental results that older children do understand this form of reasoning as well. Yeah.
Super quick question. Do you know anything about this cross-culturally? Like, has it been
No, I don't think we do. Sydney would be a better person to ask that question to, though. Okay, so now let's think about this, all these different kinds. So here we have a kind of tragedy of the commons situation, right? And maybe universalization is one way of helping us figure out what the right thing to do is. So overfishing, right? This is kind of one type of tragedy of the common. And then as Joel introduced, right, we have this huge body of work, Eleanor Ostrom and her many students and collaborators looking at institutions for actually making these tragedies less tragic, right? We actually find ways of finding sustainable cooperation. Overgrazing, another kind of classic case from this literature. You have a nice field, and then each player, or each person's choosing, should I let my sheep go graze on the common? But if they all do it bring too many sheep, the grass is dead, and then all the sheep die, right? So bad outcome. This is other work from Robert Ellickson, Order Without Law, looking at, I think these are like, basically, I guess they're cowboys or like herders in California, Central California, and all the kind of bottom-up norms and institutions that they've developed to kind of police each other. I think it ultimately was kind of a sad story where like big farming came in, and it used to be like, if you bring too many cows, you're not invited to like the party at the saloon, and then that's enough of a bottom-up mechanism. So that doesn't work when like the big corporations come. Okay, so and then now we're faced with maybe the ultimate tragedy.
That book on Amazon are hilarious because people are like, the author is so friendly to the big ranchers or whatever.
Oh, right.
Super angry at the author.
Oh, really?
It's super funny.
Oh, interesting. I didn't know that. Oh, I need to check that. And then this is maybe the big challenge of our time of climate change, and the fact that we all want to pollute because that lets us make lots of cool stuff, right? But if we do that too much, we're going to like destroy the world. Okay, so this is a paper that we found out was just accepted to NeurIPS yesterday on a project we're calling Cooperate or Collapse, and it's studying these kinds of problems in a society of generative agents, the exact kind, or not the exact kind, but very similar to the kind that Joel told you about. So I'm going to leverage a lot of his background, the background he gave in discussion, and I took this photo during his talk at the end. And I just wanted to highlight this one. There will still be many ways to do this kind of research incorrectly, so I think this is. I would also say, this is a very new area. These are kind of initial explorations of what happens. Okay, so we have 3 scenarios: some fisher people that share a lake, shepherds that share a pasture, factory owners that share a river. That kind of get it, allow us to kind of study some amount of variation. I'm going to go quickly through this just because Joel did a great job introducing it. We have, the different Ostrom principles, and we developed these scenarios because at least some of them are relevant, because we're going to have a bunch of agents interacting in a relatively open world kind of setting. Unlike in Joel's case, where there was this game master, in our strategy, they're interacting with a fixed environment that we fully control, that is, game theoretic and has parameters that we can directly study that an LLM is not in control of. And we, again, use that generative agents framework from Park et al., right? So the idea, we're going to take an LLM and give it some extra kind of structure to allow it to act in an agent-like way. We give them some personalities, some names, and I'll show you the kind of underlying cognition we give them. It's very simple, but actually quite effective and interesting. So the way the simulation runs is that we're going to look at this over the course of 12 months. And every month, agents observe the state of the lake in the lake case. They choose how many fish they want to take, and then they discuss amongst themselves based on what happened, and then they go back, reflect, store some memories, distill, and kind of update their knowledge, and then go from there. Okay, so the pond starts out with 100 fish, 100 tons of fish, and every month the population at the end of the month doubles. So if there's 50 or more fish in the lake, at the end of the month, it will double back up to 100. But if there's only like 30 fish in the lake, it'll double back up to 60. So if you don't get up to 50 and you keep overtaking too much, you're going to quickly you'll get to 0. Or I think at 5, we clip it to 0. Population is extinguished. Yeah.
And again, the agents know that.
The agents know all of that. Yeah. Well, oh no, sorry. They don't know they know all the dynamics, but we don't tell them, hey, you better be careful because if you do this, the resource will be extinguished. So they have to, but they observe what happens in previous months. So they have to collectively come to that realization, or to some extent. Okay.
But they also know it's fishing and other kind of stuff in their language models, right?
Yeah. They're literally told you're a fisherman, and you're on the lake, or you're a shepherd, and here's how the herd works, and at the end of the month it's going to double, and they're told all the dynamics of the environment in natural language. Okay, so here's what their kind of like prompts look like, just to give you a little bit of a flavor for this. So we call this the act, discuss, reflect framework. In act, basically the agents, they can either take an object, move, speak with someone, but really the key part is, they decide how many fish do they want to catch based on, and then they have this like big log, all the things that has happened in the environment, very similar to what Joel was showing. And then in reflect, at the end, they kind of can update and add new things to their key memories. So we asked the model, what high-level insights can you infer from the above statement? So they see all the memories, and including the log of that month, and then they basically have to compress that into something smaller to store in their memory. Okay, so retrieve memory and create new memory concepts. All right, so here's an example of what that looks like. We start off with 100 fish. One person catches 40 fish, and everyone's going to catch some. Then they're like, hey, how come Jack caught more fish than the other villages? Discuss. Then they reflect. Or Jack goes back to preserve the fish in the lake. I should fish much less next time. And this goes on and on. The state updates. There are 38 tons of the fish, tons of fish in the lake. Now he catch a lot less. Okay, we are going to stay low to restore the fish population. That's at least conceptually what this is going to look like. So we have this community of AI agents. We have a bunch of different resource sharing scenarios, and then we want to look at kind of what the outcome is. The agents cooperate and sustain, or do they cause the resource to collapse? And I like to think about this as a kind of like emergent mechanism design. Typically, we think of mechanism design being from the top down, like we or a government or a policymaker as a mechanism designer decides how to structure an interaction in order to get a desired outcome. But here it's all bottom up. It's can a group of agents acting together figure out a way to constrain their own behavior to achieve the outcome that they want. And because of the ability to kind of debate, negotiate, discuss in natural language, that's actually a possibility, or even sanction each other. And we're looking at that possibility more in further studies. Okay, so what actually happens, we test this with a bunch of different LLMs, and what we basically find is that overall, no models really cooperate well. The best model only survives that full year, less than 54% of the time, and we measure a bunch of other things, but in general, kind of the overall trend is the better, bigger models do better in this task. And I think one contribution that I like from this project is like, okay, well, is that it? Like you told me 54%, but new models are coming out every day. And I think what I like about what we did here is we then looked at what are the determinants of success in this game. And we looked at kind of 3 different pieces: reasoning ability, communication, and morality. And reasoning, we basically just developed our own little benchmark of some reasoning problems, but in the domain that the agents were performing in. So like, hey, if the fishermen catch M tons, how many tons of fish will there be next month, right? Where we can vary N and M, create a whole set of reasoning problems. And we basically find that across these our kind of homegrown reasoning score test, we find a kind of nice correlation between how well you do in kind of simple reasoning problems of this form and how the amount of time you survive in the social dilemma, right? With, of course, the better models doing better. But we're explaining some of the individual variation across models. Yes?
Have you considered putting some punishment into
We have considered that, but here, it would all be kind of emergent and bottom up. We don't have an explicit punishment mechanism built into the game yet, but that's really the next step for us. I'm gonna pause questions because I only have 5 minutes. We looked at communication. What if they can't communicate? Without communication, you do a lot worse. And then this is why I showed you universalization, right? What if agents ask themselves before acting, what if everyone did what I'm about to do, right? So given the current situation, we just say, if everyone fishes more than X tons, the lake population will shrink. And that actually was able to increase the survival time of the average agent more than 4 months using this special prompt. So I think there's something nice here. We're seeing kind of a convergence of mechanisms that humans are using for solving these kinds of common pool resource problems, and the same kind of mechanisms seem to influence large language models. We also have some really preliminary results on like norm robustness. What if a newcomer joins that doesn't see all the past negotiations? So this is like, how robust is your emergent mechanism? We have some, overall, I would say it totally screws everybody up. But here's one like cherry-picked example where it like was a really beautiful recovery. You can see the newcomer comes in and they fish as much as everybody else combined. So that plummets the population, but then there's some discussion here happening, and you can see the red kind of gets down, and by the end, the population is restored, and they're all kind of in a sustainable regime. Okay, let me quickly wrap up, and we're almost out of time. So I introduced two new challenges for the emergence of and the maintenance of cooperation: this game-generating environment and GovSim, which is what we call the environment for studying LLM-based agents for emergent mechanism design. And I think one, especially if you're kind of coming from a more formal or mathematical background, you might ask, well, okay, you studied these harder problems, they're more general challenges, and yeah, okay, you showed some solutions to them. You built these more general cooperative agents, but you have this more complex environment, you have this more complex agent. What are you getting? And I think what I would hope to show here is that we didn't just find a more complex solution to a more complex problem. We actually also built more powerful solutions, right? We found that the agents that could succeed in the game generator could also do even better in the prisoner's dilemma. And I think similar kinds of things here, agents that have better capabilities and capacities for cooperation in this GovSim, this government simulation, also were more powerful. And I think this is kind of a key area to push on as we try to build more capable agents for cooperative AI and safer AI-human interaction. So the reverse engineering, understanding how humans work, but then also building better and more aligned AI systems. In the last minute, I'll just plug the lab at University of Washington, recruiting students, postdocs, RAs. Reach out to me if you want to collaborate on any of these kinds of projects. Thanks.